Hello, today we are going to be presenting our project, Estimating True Chess Skill and Detecting Player Anomalies. The learning problem we address is the increasing difficulty of detecting cheating and smurfing in online chess. Over the past few years, platforms such as chess.com and Lichess have reported rising cases of engine-assisted cheating. And one famous example that I can bring up was the Magnus Carlsen versus Hans Niemann controversy, which highlighted how difficult it is to reliably detect suspicious play. Traditional systems, such as the Reagan system, compare each move to engine evaluations to estimate whether a player is performing above their expected strength. However, these systems are mathematically rigorous and they're computationally expensive. And sometimes they struggle with edge cases like Smurfs or rapidly improving players. In our project, we explore whether modern machine learning and neural networks can complement these traditional methods. Our goal is twofold. The first aspect we're going to be going over is predicting a player's true skill level, their ELO, based purely on their game data. And the second aspect is detecting anomalies, so games that look suspiciously strong, inconsistent, or engine-like. This becomes a machine learning problem because both tasks, rating prediction and anomaly detection, map naturally to supervised and unsupervised neural network methods. I'm going to go over the datasets that we used for our project. So the first dataset we used is the 60,000 plus chess game dataset off of chess.com. And the second one is chess game dataset off of Lichess. And both datasets contain player ratings, moves, openings, and metadata, and they're both used in phase 1 to train our ELO prediction network. The next two datasets we have is Cheating Tuesdays, chess.com, and Stockfish. And the second one is Spotting Cheaters, chess cheating dataset. The Kaggle Cheating Tuesdays dataset contains games flagged or suspected for cheating, includes both moves, sequences, and metadata, and is used for supervised classification in phase 2. The Spotting Cheaters chess cheating dataset contains engine-evaluated metrics such as centipede loss. Centipede loss is basically the accuracy of players' moves, and it helps with improving anomaly detection. These datasets are pre-evaluated by Stockfish, includes best move match and complexity measures, and are also used for unsupervised autoencoders. Now, I'm going to be going over our neural network design overview. We divide our neural network system into two major components. So we have our part 1 or our phase 1, which is our ELO prediction network. So for our ELO prediction network, we are building a fed-forward neural network, MLP, that predicts a player's ELO based on the move count, opening, accuracy, blunders and mistakes, rating difference, and other game-level features. This model gives us a predicted skill estimate, and large gaps between predicted and actual ELO often indicate smurfing or inconsistent play. For our part 2 or phase 2, we're doing anomaly detection, implementing an autoencoder, an unsupervised neural network that reconstructs normal human play patterns. And with our autoencoder, if we have a high reconstruction error, it means that it's a suspicious game. The second thing we are implementing is a cheating classifier. It's basically a supervised model using labeled Kaggle cheating data. And lastly, we implemented a combined detector. It's basically a weighted score using results from both the autoencoder and the classifier. And this combination gives us the strongest detection power. So out of the 3 things we implemented, the autoencoder, cheating classifier, and the combined detector gives us the strongest detection power. This is our ELO prediction model for phase 1. So for phase 1, we used approximately around 60,000 chess games, and we pre-processed the data by keeping the columns that we need, the columns that are most important. So if I were to scroll down, we first load the data sets. We do some data standardization, so we pick the key variables from both data sets and then we standardize them. And then here we do some move feature extraction. So given the moves, we extract the relevant information. So this is how we keep the key columns we need. And then here are some of the key columns. From there, we're going to encode categorical variables. So we do some simplified categorical encoding. After we get our optimized feature set, we get our numeric features. So these are the features that matter the most after we do encoding, after we encode categorical variables. Then we're going to scale the numerical features. So here we're removing the rows with missing targets, preparing a feature matrix, and we're filling in values that are needed to be filled, and removing any values that don't make sense to be there. Then from there, we're going to be working on training our model. So in our model architecture, we have 3 dense layers. So it goes from 128 to 64, then to 32. These dense layers are our fully connected layers. We also have our rectified unit layer activations that help us simplify calculations and accelerate learning. From there, we do some training our model. And as you can see, over a number of epochs, the mean absolute error values slowly climb down from 1,000 all the way down to 80. And same with the RMSE. So it goes from 1,390 all the way down to 131. And the best value we got was around 81 to 80. And this basically means that on average, our model's values are off around by 80 units. Then we go through some shapes and visualizations. And as you can see here, after a number of epochs, the value of MAE and RMSE go down, so the value of error just goes down. Then we have our predicted rating and our actual rating. So as the actual rating goes up, the predicted rating also goes up. Here, the plot shows the residuals are tightly centered around 0 with a small spread, meaning that the model is generally accurate and does not show strong systematic bias. This chart here shows that the prediction error increases as player rating increases, meaning the model performs best on lower rated players and struggles more with higher rated players. Lastly, moving on to phase 2 for anomaly detection. Phase 2 basically goes over 3 things. We have the autoencoder, which is basically our unsupervised anomaly detection. We have our supervised classifier, basically using labeled cheating data, and our hybrid approach. After training our autoencoder and our supervised classifier and our hybrid model, the reason why we combined is because the autoencoder is great at identifying unusual engine-like play. The classifier is good at confirming standard fair play, and together it would be best of both worlds, right? So if we were to combine the results, we get a highest overall accuracy, we get best cheating recall, and we get the most stable anomaly ranking. In summary, the autoencoder detects suspicious moves, the classifier verifies if the game is likely human, and the combined model provides the most reliable cheating detection signal.
Quickly reviewing the results, we can see that both the autoencoder and classifier converge successfully, and with the ROC, which is the ratio between true positives and false positives, both the classifier and hybrid perform nearly perfectly. Matrices, we can see that the hybrid model performs the best with an accuracy of 98.9%. Most importantly, we can see the false positive rate is nearly 0. This is very important as we don't want to classify someone as cheating when they're not. Similarly, looking at Cohen's distribution, we can see that there is minimal overlap between clean and fair play versus cheating. So this means that the predictions are very confident from our model. Guide through of how this would be deployed in real life. So this would have to be done on server side, for instance, by chess.com or any other provider. So in the front end, the user plays the game. Once they're done, backend will then once it's completed the game, run it through the machine learning model. So first it goes through phase 1, which is estimating the ELO, and then given that, it's going to then use our autoencoder and classification neural network to detect whether it's not cheating. And given our confidence threshold, if it's highly confident, it will ban the player. If it's unsure, it will report it to an admin for human review, and if it's not cheating, then it'll log the game, update stats, and update the central repository.
Here's a quick example of this in deployment. So I'm on chess.com and this would be running on server side. So I'm going to export one of the games I recently played, download the .pgn file, then copy it into my game.pgn file, and I'm going to run the script that loads both models and estimates my ELO as well as whether I'm cheating. So after doing that, I get the result. It gives my ELO as well as it claims that I'm not cheating.